All right, greetings folks. Hello from the back of the camera. We are now moving into chapter 14, and I think the structure of this is going to get a little bit easier. So you can see there on the side the stuff you want. I'm actually going to suggest that you maybe stop the video here in a second, and I'll come out in front. So, well, maybe I'll come out in front now. Maybe it's easier just to actually see my gestures. Real professional, as usual. Okay, so hope everybody's hanging in there, and I'll put up announcements and things like that on D2L, so we'll do a lot of housekeeping here with these videos, because I think we're in a groove. So we're in chapter 14. We're going to take these videos probably one section at a time, because it seems to work out that way. So we're going to do section 14.1 with this video, which is introductory definitions for acids and bases. So you'll want that section out of your book. The chapter 14 problem set number 1 is what you'll also want. Now that problem set is divided into 3 subparts, 14, 1, 2, and 3. It's pretty straightforward. The chapter 14 slides you should already have on D2L, and I'm chopping those up on a week-to-week basis as well. And I don't know if you're going to need it today, but your appendices, and there's 2 appendices that will be helpful here. They're called ionization constants or something like that for weak acids, and ionization constants for weak bases. So you may just want to have that handy. I'll probably upload a table anyway for you to use, but you may just want those. And if you're looking at the electronic slides that I use for lecture, like usual, the first slide is always just straight up definitions, just to kind of do that, and then we get into the math. It's pretty much what we've been doing all year, if you've had me all year, or at least this semester. So this is Roman numeral 6, acid-base equilibria, chapter 14. So if you want to, you can stop the video and just write down all the definitions on that first slide if you want. If you want to kind of go along, because what I'm going to do is streamline this a little bit. So if you want all the definitions, then I'll just put all the examples up here, rather than going one by one, one by one, one by one. I think it'll actually be a little bit faster, and since you have the video and the section in the book, you can go back and supplement that if you wish. So that's no problem. So if you want to, stop the video, take down the definitions, and then come on back. Okay, boom, we're in our magic time machine, and you either did or didn't do that. And that's okay, it doesn't matter as long as you get there. Probably need to get a new eraser. Okay. And also here, it's not that it matters to you right now, but it's rather early in the morning that I got up to come here and do this, so I'm drinking a little coffee. Okay, so definitions of acids and bases. The first set that you know, and I'm going to see if I can streamline this a little bit. So we have 2 different kinds of definitions that we're using here. Oh, there is a third definition that I give you. It's the very last, letter C, I guess. These are called Lewis acids and bases, which are based on electrons being donated. I'm just giving you that definition because that's something that a lot of you are going to see in organic chemistry. That is a really powerful definition. But I'm not going to talk about those here. So Lewis definitions, you can write it down. We can go maybe through some examples later, but I doubt we will. The 2 ones we want to make a distinction are, actually has that little accent through though. So Arrhenius definitions and Bronsted definitions of acids and bases. And fortunately for Arrhenius, you actually already know these definitions. Incidentally, Arrhenius is that Swedish chemist that we've talked about before. And so we have an acid and we have a base, and you can see the definitions on there. And yeah, okay. So an acid is something that gives H plus in aqueous solution. This is all aqueous solution, by the way. And a base gives OH minus in aqueous solution. And then we apply the definitions that we already know, strong and weak. So a strong acid gives a lot of these because it completely dissociates. A weak acid only gives some of those, very small amount. So those definitions still apply. And we've already seen examples here. Maybe this will actually look pretty organized. And to save some time, I'm not going to write AQ on all of these examples. I think it's understood now that these are aqueous solutions. Okay, so that would be an example of a strong Arrhenius acid. A weak one we've done many, many times is acetic acid. And that's a true equilibrium. So that's an example of a weak Arrhenius acid. And one I just want to bring up here, sometimes acids give off more than one H plus, and those are called polyprotic. These are called monoprotic. You also have things like mono and dibasic. And I've used examples before of sulfuric acid, H2SO4, so diprotic. I want to show you another one here. Phosphoric acid, which if you look at the side of a can of soda, you'll look at that. There's a lot of phosphoric acid in soda, which is not really all that good for you. This actually is a triprotic. So it'll give off one, but then it'll give off another one, so that ion then comes down and then it actually happens a third time. This actually has to be 2 minus. So that actually will give off H3PO4 in steps, will give off hydrogen. So this is actually called a triprotic acid, or more in general, polyprotic. So you have monoprotic and polyprotic. Di, tri, and that's really about all we're going to deal with here. So those are some examples. Examples of Arrhenius bases, we've already seen some of these. Again, I'm not writing aqueous. Oops, that's incorrect. So that would be an example of a strong base. And I think we did this one before. Sometimes it's not just simple dissociation, sometimes it's actually to get the OH minus, there's a reaction with water. And this is an example of a weak base. So these are the Arrhenius definitions, which we've already done these definitions before. And I just want to double check to make sure that we're getting those. So we've done those. That's really nothing new. In fact, what I want to do now is then show you the other set of definitions. And these are called Bronsted-Lowry. I think I'll have enough room there. I'm going to erase some of this, just because I want to make sure I have enough space. Okay, so when it comes to Bronsted-Lowry definitions, what we have there, we have to think of things in pairs. And I'm actually going to wing this a little bit here. So if you look at the definitions, a Bronsted acid is really the same thing. It donates a proton. So an acid's still the same thing. It's an H plus donor. And a base is an H plus acceptor. So we actually have to think about the things together. So let me just show you an example here. It doesn't break down into acid-base. We actually think about them in acid-base pairs. So rather than two separate categories, we think of them together, which actually makes a lot of sense. Okay, so you already have the definition. So acid is an H plus donor, a base is an H plus acceptor. Let's just look at an example. And I actually want to use an example we already used. Again, everything here is aqueous. So the goal here is when you look at an acid-base equilibrium, what's the acid and what's the base? Well, in this case, we've already done this. This is the Arrhenius base. Why? Because when it reacts with water, it gives you OH-. Well, that's fine. Well, what's actually happening in this reaction? Well, NH3 is accepting an H plus from the water. And water is left behind with OH minus. So in this case, see if I can get this right. This is an H plus donor. This is an H plus acceptor. See that? Because when this accepts an H plus, it turns into this. When this donates the H plus, it turns into hydroxide. So this is the Bronsted acid. This is the Bronsted base. Fine. It's really not that big of a difference. The thing I want to toss in here, I think we have this. Yes, okay. We'll get to this later. So, if we actually consider this in the reverse direction, remember equilibrium, we have to think about things in the reverse direction. Well, they would be the opposite, going in the reverse direction. If we went in this direction, it'd be the ammonium plus ion, that would be the H plus donor. And the OH minus would be the H plus acceptor. It's the exact opposite, it's not that hard to do. So it's a Bronsted base here, it's a Bronsted acid here. This is called the conjugate acid. This is called the conjugate base. I like these definitions because it ties the two together and it makes it an equilibrium as well. So H plus acceptor is a Bronsted base, H plus donor is a Bronsted acid, and then we talk about acid-base pairs. So NH3, NH4 plus is a Bronsted base, Bronsted acid pair. Sometimes called conjugate acid-base pairs or base-acid pairs. It doesn't really matter which way you do it. Then water and OH minus is a Bronsted acid, Bronsted base pair. See how that works? It takes a little bit of time to sort this out because you have to think about things, what's actually happening in the chemical reaction. Okay, so there's examples in your book as well. Let's do one more just to get the basic definitions down. Oh, okay. Yeah, this is a different one. The ammonium ion, which we could get from something like ammonium chloride or something like that. Kind of similar to this one, but so ammonia is a base here, ammonium is doing something different, I don't want to give it away. So just take a look at that for a second. Which one of these is the Bronsted acid? Which one is the Bronsted base? And then which one is its conjugate acid-base pair? So if you wanted to think about that for a second, stop the video, see if you can do it on your own. Stop it. Okay. So in this case, the ammonium is giving, it's giving an H plus to the water, and then it ends up being ammonia with a neutral charge, going from +1 down to neutral. So this is the Bronsted acid. Well, if that's the Bronsted acid, everyone has to be the Bronsted base. It has to be, because it has to by default. But is that exactly what's happening? Yeah, okay. That's accepting it. And if this is the Bronsted acid, this is the conjugate base of ammonium. And if this is the Bronsted base, this is the conjugate acid. Okay, Okay, get the idea? So what I'd expect you to be able to do is to take a look at an equilibrium, figure out which one's the conjugate acid, which one's the conjugate base, and which one's the Bronsted base, Bronsted acid, and then their corresponding conjugates. So those are called conjugate acid-base pairs, being able to identify those. That's not too tough, those are definitions. Oh yes, and there are some, this is actually kind of interesting, some molecules can actually be either an acid or a base, depending on how they react. So that's called amphoteric. Yeah, well actually we have a couple more examples here. So think about that for a second. I'm going to give a couple more examples of Bronsted acid, Bronsted-Lowry acid base pairs. They're just kind of interesting. And we're going to come back and use these later. So that's 2. Number 3. I didn't really rehearse this video, can't you tell? Something we don't really talk about. Water, H2O, can actually split up into H plus and OH minus. It doesn't do it very much. It's an equilibrium that favors the reactants, water, which is good, because if most water broke up into its ions, that wouldn't really work out too well for us. And that's called auto self-ionization, which you already know. So this water, believe it or not, will actually react with itself in a very, very small amount. I'm going to show you the equilibrium constant here in a second. It's a very small equilibrium constant. So this happens. This actually does happen. This is a strange one. Now we have to remember which water is which. So if you want to figure out which water is the acid, which one's the base, like maybe match this one up with this one and this one up with this one. Okay, so this water, if it's the second one, is the H plus donor because it's giving it to this one. This is the H plus acceptor, so this is the Bronsted base. This would be the Bronsted acid. Then this would be the conjugate base of the acid, and this would be the conjugate acid of the base. So if we went in the reverse direction, we would just flip it around. That's a neat example. I might as well throw this out there. The K equilibrium constant for this reaction, you might remember that we don't consider solvents when we write this. So there's so much water that we ignore the H2O in the K expression. This is actually given a special name, KW. The auto dissociation constant for water. We're going to use this quite a bit. It's in an aqueous solution. It's the H3O plus concentration times the OH minus concentration. That's actually, there's a shorthand for this. H3O plus is chemically equivalent to this. It's a shorthand. So, at 25 degrees Celsius, this actually equals 1.0 times 10 to the minus 14. So it's a really small equilibrium constant. So what does that tell us? Well, that tells us that this equilibrium lies heavily to this side and not very many ions form here. This is actually a really handy equation to know. This relates the acid content of an aqueous solution to its corresponding base content. And I don't know if you've looked ahead a little bit, you might know the pH scale goes from 0, or actually it can be negative, 0 up to 14. This is one of the reasons why the pH scale goes up to 14 is this constant here. We'll get to that math a little bit later, it's not too difficult. So I'm just sneaking that in on you now. Okay. Oh yeah, let me show you one other example. Actually, no, I'm not going to do that. So those are examples of Bronsted-Lowry acid-base pairs. The last one I want to show you, because we're going to use it so much, is some substances act as both acids and bases, which is really important in your body to keep your body buffered. And we're going to learn a little bit more about buffers. Most of you are going to learn about buffers in lab. I don't think we're going to do a ton with buffers in lecture because of time, so we'll push that one to the lab. But buffers absorb acids and bases and keep a constant pH level, which is really amazing how they do that. So something that is amphoteric, meaning it can be either an acid or a base, and I have two examples for you here. This is a very important ion in environmental systems and in your body. It's the bicarbonate ion. You might have this in your kitchen if you're at home. This is baking soda. Sodium bicarbonate is baking soda. The sodium is a spectator ion, sodium +1. So that's what you would use here. So just to give you an example, bicarbonate can actually be either an acid or a base. And this is good practice. Okay, both of these reactions, both of these equilibria actually occur. Believe it or not, they occur simultaneously. You can't have one without the other. I'm not going to worry about that right now. But if you want to, stop the video and see if you can identify the Bronsted acid or base here and here, and then the corresponding conjugate acid bases over here. So you're identifying your acid-base pairs, conjugate acid-base pairs. So if you want to, go ahead and stop the video. Okay, we're back in time. So in this case, I'm not even going to give the explanation here. So, gives the H plus there. Yeah, okay. So this is going to be the conjugate base of bicarbonate. This will be the conjugate acid of water. Yeah, so carbonate is the conjugate base of bicarbonate. Okay. And then H3O plus, hydronium protons, H plus symbol, that's a shorthand for that. That's the conjugate acid of water, which actually runs that base there. Fine. In this case, I think it's the exact opposite. So this is the Bronsted acid, because it's giving an H plus over here. So this is the Bronsted base. This is going to be the conjugate acid going in this direction. This will be the conjugate base going in that direction. Okay. But since bicarbonate can do both be an acid or a base, that's called amphoteric. And water is also amphoteric. I don't think I need to go through that example here. Well, because it's being both an acid and base there as well. Okay, so it just depends. Actually, this example also shows that water can be a base or an acid. So we kind of kill two birds with one stone there. A little violent image, but you get the idea. And Lewis definitions, I'm actually going to skip those. I don't think we need to do that for this one. And last I checked, folks, I think that's it for definitions. So know your Arrhenius definitions, know your Bronsted-Lowry or just your Bronsted definitions, and be able to identify them. And now we're going to go into the math, is how do we use some mathematics to describe acids and bases, probably starting with something familiar to you, namely the pH scale. So that's section 14.1. Go back, read section 14.1, do all the check your learning problems, do some of the homework problems that go along with that as the week progresses. This is a really good week to do 14.1, done, 14.2, done, and then keep moving. Okay, that's it.